We can also perform inverse substitutions. What we did before with a direct substitution was we replaced the variable of integration or a function of the variable of integration by a new variable. So direct substitution, there we introduced the new variable u, which was a function of x, so it was a function of the original variable of integration x. The goal was to simplify the expression in that way and find an easier solution for the integral. For inverse substitution, we do the opposite. So here we will not replace a function of x by u, but we will replace the variable itself, so replace the variable x by a function of u. Normally you would say that this will make your integral more difficult, more complex, but we will see a number of cases in which this method will simplify our calculations. The first group of inverse substitutions are the inverse trigonometric substitutions. In this case, we will replace the variable x by a trigonometric function. So we will set x equal to a times sine of theta, or x is a times tangent of theta, or x is a times the secant of theta, depending on the case. So these are the inverse trigonometric substitutions, and these correspond to the following direct substitutions. So x is a sine theta is a direct substitution of theta equal to sine inverse of x divided by a. And then the others are similar, so theta is the tangent inverse x divided by a, or secant inverse x divided by a. Where secant inverse x divided by a is the same as cosine inverse a divided by x. The question then is, when do we use these substitutions? The first case is a case where you have something a squared minus x squared, and we will always assume that a is positive. In this case, what you will use is x equal to a sine of theta. Why would you use this substitution? Well, if we plug it in, we get here a squared minus a squared sine squared of theta, and then we need to take the root of that. So a squared times 1 minus sine squared is a squared times cosine squared. So this is just a times the cosine of theta. So we simplified the expression into a simple trigonometric function. Let's apply this to an example. Let's say we want to calculate the integral of 5 minus x squared to the power 3 over 2 dx. So here this 5 is equal to a squared, which means that a is equal to the root of 5. So the substitution that we will be doing is x equal to root of 5 times sine theta. In this case, dx is root of 5 times cosine theta d theta. And then we plug this into the integral. So we get this is 1 divided by 5 minus 5 times sine squared of theta to the power 3 over 2 times the root of 5 cosine of theta d theta. We first take out the constants, so in the numerator we have root of 5, in the denominator we have 5 to the power 3 over 2 times the integral cosine theta over cosine theta to the power 3 d theta. So this is 1 over 5, the integral of 1 divided by cosine squared of theta d theta, which is 1 over 5, the integral of secant squared of theta d theta. So this is 1 over 5 times the tangent of theta plus a constant. What is left now is to transform this back into an expression using x. For that we will use trigonometry and we will take a look at the triangle, at the right angled triangle based on x equal to a sine theta. We know we can calculate the sine as the opposite side divided by the hypotenuse. And so the triangle that we become using x equal a times sine theta is the following. This means that the final side has a length of a squared minus x squared and then the root of this value. Since we now know all three of the sides, we can calculate the cosine of theta and the tangent of theta as well. So cosine of theta is the adjacent divided by the hypotenuse. So it's the root of a squared minus x squared divided by a. The tangent of theta, this is just the opposite divided by the adjacent. So x divided by this root. Here we need the tangent, so the tangent is x divided by the root of a squared minus x squared. So finally my integral becomes 1 over 5 x divided by root of 5 minus x squared plus a constant. For the second case, consider expressions which use the root of a squared plus x squared or something with 1 over a squared plus x squared. Again, under the assumption that a is a positive number. The transformation that we will be using is x equal to a tangent of theta. And in that case, a squared plus x squared becomes a squared times 1 plus tangent squared of theta. So it's a squared times secant squared of theta. Also here we will need the triangle at the end to find the different trigonometric functions. So we can make a triangle using x is a tangent theta. And we know that the tangent of theta is the opposite divided by the adjacent. So the triangle that we obtain is the following. So using this triangle we can also find sine of theta. Sine of theta would be x divided by the hypotenuse, so the root of a squared plus x squared. And the cosine of theta, this is the adjacent, so it's a divided by the hypotenuse, root of a squared plus x squared. Take, for example, the integral of dx divided by 1 plus 9x squared to the power 2. To get this in the correct form, we first take out the 9 from below, so it's 1 over 81 times the integral dx 1 divided by 9 plus x squared to the power 2. And now we can do a substitution, so x will be 1/3 of tangent theta and dx is 1 over 3 times secant squared of theta d theta. We then plug this into the integral, so it is 1 divided by 81 times 1 over 3 secant squared of theta d theta, and then below we have 1 over 9 secant squared of theta to the power 2. If we then simplify the expression, it is 1 over 3, the integral of secant squared of theta over secant to the power 4 of theta d theta. So it is then 1 over 3 times the integral of 1 over secant squared, so cosine squared of theta d theta. Then we saw previously with the trigonometric integrals what the integral of cosine squared is. So this becomes 1 over 6 theta plus sine of theta times cosine of theta plus a constant. And then finally we have to replace the thetas. So this is 1 over 6. Theta is the inverse tangent of 3x. So this becomes tangent minus 1 3x. And now we have to use the formulas for the sine and the cosine. And we use then that a is 1 over 3. So we get the sine, this is x divided by the root of 1 over 9 plus x squared times 1 over 3 over the same root. Which then becomes 1 over 6 tangent minus 1 3x plus 1 over 2 x divided by 1 plus 9x squared plus a constant. And then the third inverse trigonometric substitution, we will use this when we are confronted with a root of x squared minus a squared. Again, a positive. So in this case, you set x equal to a of secant theta. With this substitution, this root becomes the root of a squared secant squared of theta minus 1. So it is the root of a squared tangent squared of theta, or a times tangent theta. In this case, the triangle looks as follows. Take then, for example, the integral of dx divided by the root of x squared minus a squared. The substitution then is set x equal to a times secant of theta, and then d of x is a times the secant of theta times the tangent of theta d theta. We then plug this in, so we get a secant theta tangent theta d theta divided by the root of x squared minus a squared, which we calculated is a times tangent of theta. After simplifying this expression, we get the integral of secant theta d theta, and this integral we calculated earlier is the logarithm of secant theta plus tangent theta plus a constant. Transforming back, so this is the logarithm. Secant of theta is 1 over cosine of theta. So we know that secant of theta is x divided by a. And then the tangent of theta we can find in our triangle. The tangent of theta, this is equal to root of x squared minus a squared divided by a plus a constant. We could even simplify a little further. We know that a logarithm of a product, so ln of a times b, is ln a plus ln b. And here we have a common factor of 1 over a. If we then take out the common factor, this is the logarithm of x plus the root of x squared minus a squared, plus the logarithm of 1 divided by a, plus a constant. But now this is just a constant as well, and so we can place it in C. And so my final solution will be the logarithm of x plus root x squared minus a squared plus a constant. Often inverse trigonometric substitution is combined with completing the square. Let's say we want to calculate the integral x dx divided by 4x squared plus 12x plus 13. The first thing that we will do is take out 1/4. So we get x dx divided by x squared plus 3x plus 13 over 4. Recall that for completing the square we use the formula a plus b squared is equal to a squared plus 2ab plus b squared. So here a squared is x squared, 2ab is 3x. So this means that a is equal to x and b is equal to 3 over 2. So b squared, the b squared that we need, is then 9 over 4. So we rewrite the integral. So it's x dx over x squared plus 3x plus 9 divided by 4. This is my b squared. And then I am left with 4 over 4, so I have 1 left. So this is then 1 over 4 x dx, x plus 3 over 2 squared plus 1. Let's then perform a substitution. So u equal to x plus 3 over 2. So du is just dx. And x is u minus 3 over 2. We replace then x by u minus 3 over 2 and we split it in two different integrals. So we get 1 over 4 u du divided by u squared plus 1. And now we have minus 3 over 2 times 1/4. The integral of du over u squared plus 1. For the first integral, you could either do a new substitution, so set t equal to u squared plus 1, or you can do it on side. So you see that the denominator is u squared plus 1 and the numerator is u. So the derivative of u squared plus 1 is 2u, so we would need a 2u here, which also means that we have to divide by 2 to keep everything balanced. This means that my integral here becomes 1 over 8 times the logarithm of u squared plus 1. And then the other one here, this is minus 3 over 8 times the inverse tangent of u plus a constant, and then we replace u again. So this is 1 over 8 times the logarithm of x plus 3 over 2 squared plus 1 minus 3 over 8 inverse tangent of x plus 3 over 2 plus a constant. Then there are also two other inverse substitutions that we will discuss. The first substitution is used in cases where we have the nth root of ax plus b, so the nth root of a polynomial. In this case, what we do is set ax plus b equal to u to the power n. This will help simplify my expression by getting rid of the nth root. Calculate, for example, the integral of x dx divided by the third root of 3x plus 2, and then between the boundaries minus 1 over 3 and 2. So we will substitute the part below the root, so we will substitute 3x plus 2, and we will set this equal to u to the power 3. We have the third root, so we take a third power of u. In this case, 3 times dx will be equal to 3u squared du, and we also have to change the boundaries. So if x is minus 1 over 3, then u to the power 3 is equal to 1, or u is equal to 1. If x is equal to 2, so this is my upper boundary, then u to the power 3 is equal to 3 times 2, 6 plus 2, so this is equal to 8, and this means that u is 2. So my integral after substitution becomes an integral from 1 to 2. X is u to the power 3 minus 2 divided by 3. 1 divided by the third root of 3x plus 2, this is 1 divided by u. And now we see that dx is 1 over 3 times 3u squared du. If we take all of this together, it gives me 1 over 3, the integral from 1 to 2, u to the power 4 minus 2u du. So this is 1 over 3 u to the power 5 over 5 minus 2u squared over 2 between the boundaries 1 and 2, which is equal to 1 over 15 u to the power 5 between 1 and 2 minus 1 over 3 u squared between 1 and 2. So this is 1 divided by 15 between 2 to the power 5 is 32 minus 1 minus 1 over 3, 4 minus 1, which is 31 divided by 15 minus 1, or it is 16 over 15. So please note that because we have a definite integral here and we have changed the limits of integration accordingly, we do not have to transform it back to x. We can immediately plug in the limits of integration for the new variable. And then a similar problem, so calculate the integral for dx divided by x to the power 1/2 times 1 plus x to the power 1 over 3. So this problem is not exactly alike, but it is very similar. Let's take a look at the denominator. So this here is x to the power 1/2 plus x to the power 1 over 6. If we want to get rid of these roots, so this is the root of x plus the sixth root of x, we need to set x equal to u to the power 6. So if we do this, x is equal to u to the power 6. This gets rid of the sixth root of x, and it will also get rid of the root of x, because that will be just u to the power 3. So in general, how do we do it? We look at the powers here. So we look at the roots that they represent, the root of x and the third root of x, And then we take the least common multiple of those roots. So here we have the root of x. We have the third root of x. So the least common multiple of 2 and 3. So this is equal to 6, this least common multiple. And so what we do is we take this least common multiple and we use this in the substitution. So we set x equal to u to the power 6. So here we use the least common multiple of both roots. Then we have dx equal to 6u to the power 5 du. And we perform the substitution. So this becomes the integral of 6u to the power 5 du divided by x to the power 1/2. So this becomes u to the power 3. And then 1 plus u to the power 2. This is then equal to 6 times the integral of u squared du divided by 1 plus u squared. Then to solve it, we use a trick that we applied before. We add 1 and we subtract 1. And so we can split the integral. So this becomes 6 times the integral of u squared plus 1 divided by 1 plus u squared. So the integral of du minus 6 times the integral of du over u squared plus 1. So this is 6 times u minus 6 times tangent inverse of u plus a constant. And then finally we have to transform it back. So this is 6 times the sixth root of x minus 6 times the tangent of minus 1 of the sixth root of x plus a constant. And then the last one. So the last one is a tangent theta over 2 substitution. And this is a very important one. When do we apply a tangent theta over 2 substitution? If we have an integral whose integrand is a rational function of sine and cosine. So we use it if the integrand is a rational function of sine theta and cosine theta. So the integrand must be a fraction which uses sine theta and cosine theta. So the substitution here is set x equal to tangent theta over 2, or if you transform it to a direct substitution, theta is 2 times the inverse tangent of x. What are then the substitutions for cosine theta and sine theta? Well, sine of theta, we can calculate this. Sine of theta is sine of 2 times theta divided by 2. Why do we go to theta over 2? Because we set x equal to the tangent of theta over 2. So this is trigonometry 2 times sine theta over 2 times the cosine of theta over 2. If we then multiply and divide by cosine theta over 2, you see this is equal to 2 times the tangent of theta over 2 times cosine squared theta over 2. This is 2 times tangent over 2 divided by secant squared of theta over 2. And then you also know that the secant squared is 1 plus tangent squared. So this is 2 tangent theta over 2 over 1 plus tangent squared theta over 2. Or it is 2x divided by 1 plus x squared. You can do a similar calculation for cosine. So cosine of theta. For this one, you know cosine of theta is 2 times cosine squared theta over 2 minus 1. Then we use the same thing for cosine squared. So cosine squared is 1 divided by secant squared, is 1 divided by 1 plus tangent squared. So this is 2 divided by 1 plus tangent squared theta over 2 minus 1. So this is 2 times 1 plus x squared minus 1. And if we then put everything on the same denominator, this is just 1 minus x squared divided by 1 plus x squared. And then finally, we also have to see what dx would be. So dx, this is 1/2 times secant squared of theta over 2 d theta. This is 1/2 times 1 plus tangent squared theta over 2 d theta. And so we see that d theta is equal to 2 times dx over 1 plus x squared. So the substitutions that we need are cosine of theta is equal to 1 minus x squared over 1 plus x squared. Sine of theta, this is 2x divided by 1 plus x squared. And then also d theta is 2 times dx divided by 1 plus x squared. Take for example the integral d theta over 2 plus cosine of theta. So this is a rational function, 1 divided by 2 plus cosine theta, which uses cosines and sines, so in this case only the cosine. We then apply the inverse transformation, so d theta is 2 times dx over 1 plus x squared. And then here 2 plus the cosine was 1 minus x squared over 1 plus x squared. This is the integral 2 dx over 1 plus x squared divided by 2 times 1 plus x squared plus 1 minus x squared over 1 plus x squared. We divide out this x squared, and so this is then the integral 2 times dx divided by 3 plus x squared. We can then calculate this integral using the formulas we saw before, and so this becomes 2 over the root of 3 times the inverse tangent of x divided by the root of 3 plus a constant, and then we have to transform back, so 2 over root of 3 tangent minus 1 of 1 over the root of 3 times the tangent of theta over 2 plus your constant.